All right, let's say that we want to, let's just say we start out with a parabola. That's a good place to start. So here's a coordinate plane, and my parabola is going to look something like this. And let's say that we're told that we want to fit a rectangle inside this parabola. We also have to be given a formula for the parabola. The parabola will be f of x equals 4 minus x squared. So we want to find the maximum area of a rectangle that's inscribed in this parabola. Now, it's important that we say that we're looking for the maximum area because a minimum area would be very easy because I can find a minimum area in two ways. One way is where the length is 4 and the width is 0, or the length is 0 and the width is 4. That gives me two rectangles with an area of 0. So that's not really hard to do. A minimum area is not hard to do. A maximum area, that's going to be somewhere in the middle. So either we can write do a little graph of the area. If x is 4, the area is 0, but if x is 0, the area is 0. So this is, if x is the width, if x is 4, the area is 0. If x is 0, the area is 0. Now, if x is a little bit bigger, then we actually get some area. So at some point, so if x is bigger than 0, we get some area. But if x is smaller than 4, we get some area. So at some point in between there, it has to level out because the area is increasing from both ways going in, from both sides going in. So at some point, there's going to be a maximum value. Now, our job is to find where that maximum value is going to be. Now, to do that, we need two things, generally two things, one of which is going to be the equation that we're going to optimize, and the other one is going to be the constraint. Well, we're trying to maximize the area, so let's say that, let's call area x times y. Now, since we're working in a coordinate plane, let's make this x and this y for our purposes. Now, for this purpose, I said that the whole base of the rectangle was the length. In this case, I'm only going to use this bit because we are technically in a coordinate system. So let's just call this x. And if we maximize this half, since a parabola is symmetric, specifically this parabola is symmetric about the y-axis, if we maximize this half of the rectangle, we're going to maximize the whole thing. So our area is given by this. Now, if I want to maximize just this formula, I could make x as big as I want and y as big as I want. So there has to be some sort of constraint, and this constraint comes from the formula for the parabola, because this has to be inside the parabola. So this is y. So I can rewrite this area formula as area equals x, but I know that y is 4 minus x squared. Given that, we can come up with a new formula, since it's a new formula, a new color. The area is going to be 4x minus x cubed. Great. So what? Well, this is actually this. This is a formula for area. If x is 0, this is 0 minus 0, and we get a 0 area. If x is 4, we have, this is going to be different. If x is 2, this is 4 times 2, which is 8, minus 2, which is also 8, which is also 0. So if we apply this idea to this, this idea of area to this idea of our variables, this would be 0 over here, and this would be 2 out here. And we can, this is actually this, where if x is 0, the area is 0, and if x is 2, the area is 0. But at some point in between, it's a maximum. The question is, where is that? Now, in this case, this is a cubic function, so this is not going to be at 1. So let's figure out where that's going to be. To do that, let's use some calculus. As x is increasing, the rate of change is increasing for a bit, and then it stops and it's decreasing for a bit. I am very much concerned with where it stops. Now, where the rate of change stops, the derivative is 0. So let's find the derivative of this function. This would just be pretty simple, 4 minus 3x squared. In doing that, we want to set this equal to 0 because we're looking for where the rate of change is 0 because that's the derivative. The derivative is the equation for the rate of change. Well, where is the rate of change 0? This is the equation. I want it to be 0 because it's increasing and it's decreasing. What goes up must come down. In order for something to change direction as far as vertical is concerned, it has to either go to infinity or stop. And in this case, we're not dealing with an asymptote, so this is just where it stops. So I set the derivative equal to 0 and solve for x, in which case 4 is going to equal 3x squared. Divide both sides by 3. 4/3 is x squared. Therefore, x is, if I want to be super fancy, 2 squared roots of 3 over 3. So if x is 2 squared roots of 3 over 3, well, what is y going to be? Well, since this is the formula, I can just say that y is going to be 4 minus this x squared is just 4/3. So instead of substituting 2 squared roots of 3 over 3 in for x squared, I'm just going to say 4/3. So this is 12/3 minus 4/3, which should be 8/3. So y is 8/3. So this y and this x are going to give me dimensions on this rectangle that will yield a rectangle of maximum area. There are no other dimensions for this rectangle where it's inscribed in this parabola such that you will get a larger area. It will not exist because we just found the maximum. All right, let's do another one. Let's say that we want a product of two numbers to be a maximum. So let's say that we want the product of two numbers to be a maximum. Product is a max, let's say. And I also want that 3 times the first plus 2 times the second equal 30. So I'm just going to write that as an equation. 3x plus 2y equals 30. So this is what this is the constraint. This is what I want to maximize. Actually, that would be very easy. No, that would not be easy to maximize because if x is 0, y could be, well, if x is 0, y would be 15, but if y is 0, x would be 10. Either way, there's got to be some better place in the middle to get a maximized product. Because if x is 0, then the product's 0. If y is 0, the product's 0. So we can come up with a formula. This formula is pretty easy. The product is going to be x times y. So in this case, what I want to do is I want to solve. So here is what I want to optimize. Here is what is constraining me. Because if I want the product to be a maximum, it'd be very easy. Just make x 17 billion and make y 17 trillion. And then you have a maximum. But I could even make it bigger than that if I make them both trillions, or if I could make them both septillions or octillions or really huge numbers. There's no limit on how big I can make x and y. So what I want to do is I want to use this constraint inside the equation that I want to maximize. So the first thing I want to do is let's solve this for y, in which case y would equal 30 minus 3x over 2. Little simplification, y is going to equal 15 minus 3 halves x. So if that's y, I can rewrite this product equation as x times 15 minus 3 halves x. Great. So this product, either x is going to be 0 or x is going to be, if x is, well, okay. So this formula is going to give us a parabola. 15x minus 3 halves x squared. All right, great. what is this? This is another parabola. Because what happens here is that if x is 0, the product is 0. But if, in this case, if y is 0, x would have to be 10. So actually, if I use 10 here, I would get 15 or 150, and 10 squared is 100, and 3 halves of 100 is 150. So if x is 0, our product is 0, and if x is 10, our product is also going to be 0, and that's just no good. So if x is a little bit bigger than 1, we're going to get a better product, and if x is less than 10, we're going to get a better product. So at some point in there, it's going to reach a maximum. The question is, where is that maximum? Well, at this point, the rate of change stops. So where the rate of change stops, the derivative is 0. So if I want to find where the derivative is 0, I first have to find the derivative. To do that, we'll use the power rule. But one thing of note is that this is going to be 5. Because this is a parabola and parabolas are symmetric. So our answer is going to be 5. But I can prove that to you. Just estimating isn't good enough. So let's take the derivative of this. Our product prime is going to be 15 minus 3x. Because if I multiply this by 2 and take 1 away, this becomes 3 and this becomes x. So if I set this equal to 0, we get 15 equals 3x. So 15 is 3 times what? 3 times 5. So x has to equal 5, which follows that. So we were right that the product is going to be maximum when x equals 5. Now, if x is 5, this is 15. What would 2 have to be? 2 would have to be 15 plus what times 2? Well, let's just solve that because I don't want to do that in my head. So if x is 5, that's 15 plus 2y equals 30. Subtract 15, 2y also has to equal 15, which means y is going to be 15 halves. So there's your y, and there's your x. There are your two numbers that will satisfy this equation and will give you a maximum value. Great. Let's do another one. Let's say that you work at Walmart and your CEO is super cranky because he got billions of dollars of tax payoffs or whatever and doesn't want to share them. So he needs a new fenced-in area and doesn't want to spend a lot of money on fence, but he told you that he needs 20,000 square feet of area. So here's 20,000. The area is going to be 20,000 square feet. And he says, hey, find me the dimensions that I only have to buy the least amount of fence, and I'll give you your cheesy $100 bonus. And you're like, sure, whatever, it's Walmart. Anyway, let's say the dimensions of the fence are x by y. So you know that the total amount of fence that you're going to have to get is going to be 2x plus y. Because one side of this fenced-in area is going to be the store. So I guess it's some sort of garden shop where there will be a door here. I don't know, something like that. And yeah, great. So this is what we need to minimize in this case. Now, this one's going to be different because if we would want to minimize this. So let's try and think of this logically. How could we maximize this? It would be very easy to maximize. Because if, let's say, y was 20,000, x would be 1. So if y was 20, well, let's say x is 1, y would be 20,000. That'd be a lot of fence, but it would be correct. If x is 0, it's impossible. So there would be an asymptote there. On the contrary, if x is 20,000, y would be 1. So if x is way out here, the area would be, it'd still be 20,000, but that's still a lot of fence, 20,000 feet of fence. Well, if x is 20,000, y would be 1, so you would need 40,000 square feet of fence. And if y is 20,000, you need 20,001. So actually, this isn't trying to scale. This actually would be way up here. So at some point in between, and there would be an asymptote here also, there would be some happy point where the amount of fence you need is a minimum. So something has to constrain this, because I could derive this right now, but I would end up with a y prime, and that's not generally a fun thing to deal with. So let's also consider that the area of 20,000 square feet has to equal x times y. All right, great. There is a constraint, and this is what I want to minimize or optimize. So I can solve this for, let's solve it for y, because generally we don't derive y, because scary. I don't know why. No, let's do x. Just change things up a bit, because we can do x. So let's say x is going to be 20,000 over y. Great. Okay, so what I can do is I can substitute this into my optimization formula, and we end with that the amount of fence we'll need is going to be 2 times 20,000 over y plus y. Great. Okay. Now, what we want to do is we want to find where is the rate of change 0, because if x is too small, this diagram uses x, we're going to use y, but I mean, they're fairly interchangeable. The formula is just going to look a little bit different. So if y is too small, we use too much fence, and if y is too big, we use too much fence. So where is that happy spot in between? If we use less than too much, it's better. If we use more than too little, it's better. All right, so that happy point is somewhere in between, and that's where the rate of change is going to be 0. So if I take this function for formula and I take the derivative of it, this would be negative 40,000 over y squared plus 1. Great. All right. Because this is 40,000 over y plus y. And the derivative of this, I could also write this as 40,000 y to the negative first power plus y. So this, I multiply by negative 1 and then subtract 1, so this is negative 2. So that's why this becomes negative and a y squared in the denominator. And the derivative of y is just 1. Great. All right, this has to be 0, because this is the formula for the rate of change now, and we want the rate of change to be 0, because that's the minimum point. So what I want to do is I want to start solving this, and that's going to be 0 is going to equal 40,000 over y squared. Great. Multiply both sides by y. Find out that y squared is going to be 40,000. Which the square root of 40,000 is 200. So y is going to equal 200. Great, that's the y dimension. Now you would assume that your Walmart boss could figure out the rest, but maybe not. So let's also say that we also need to figure out what x is. So this, since y has to be 200, what is x going to have to be? Well, 200 times what is 20,000? We can write this out. Say that 20,000 is going to equal x times 200. If I divide both sides by 200, I get that x is going to equal 100. So altogether, how much fence is going to be needed? 400 feet of fence is going to be needed. 400 feet is needed. Now, that's the least amount of fence you would need. That's much better than 20,002 and 40,001 feet of fence. So 400 is a lot better than both of those, I would think. Pretty sure. Yeah. All right. So the idea with these is you need, there's a couple steps. First of all, you need 2 equations. One to optimize and one to constrain. Constrain. Because if there was no constraint in this problem, I would just say, well, don't buy any fence. That's a very little amount of fence. But the constraint is the area has to be 20,000. In this one, I could say that, well, I could just make these numbers really huge. Well, there's a constraint. In this one, I could just make, what do we want to do? We want to maximize the area. Well, I'll just, again, I'll make, wait, that's not the one we worked on. Here it is. This one. I'll just make these numbers really big, and that'll be a giant rectangle. Well, no, there's a constraint. Each time there's going to be a constraint. So you need, what are you going to optimize and how is it constrained? So step 2 would be combine the two formulas. Combine the formulas. Because that's what is going to give you a formula of one variable. In the fence problem, which is here, we took the fence formula and we substituted the area formula into the fence formula. That way we had a formula for fence that was only one variable. That's easier to deal with. So that would be step 2. Step 3 would be to derive the formula. Derive the new formula. So the new formula is the one that's the combination of the two. The 4th step would be set that equal to 0. The 5th step would be solve for the variable. I like using x's and y's because I think that's simple, but if you wanted to use, like for the rectangle problem, if you wanted to use length and width, that's fine. You don't have to use x and y. So I'm just going to say solve for the variable. So once you have that variable, step 6 would be to answer the question. Answer the question. Because just because you know what one of the variables is doesn't mean you're done with the problem. Your Walmart manager needs to know everything because they can't figure it out themselves. Yeah, so make sure you answer the question in the end. So there's 6 steps to solving optimization problems, and I did 3 of them. I think that's pretty good. 22 minutes isn't bad.